Good morning. Welcome back to Physics 4B Lab. We are moving on with another one of our labs in thermodynamics. So last week or a couple of weeks ago we were looking at specific heats, and now we want to take a look at our latent heats. So remember, specific heats are related to temperature changes in a material. Latent heats are related to phase changes. Now we're going to work with a familiar compound today. We're going to be using water, and we are going to keep track of how much heat is involved in melting water, right? If water melts, how much heat went into the ice in order to convert it into water? Now when it goes from ice into water, it remains at 0 Celsius during that phase transition. So what we can do then is set everything up on the board. Now, if this board looks a lot like the specific heat lab, it's because this lab's a lot like the specific heat lab. This is the latent heat lab. And you're going to see, though, that the data tables and the setups look pretty similar. We have our friend, the calorimeter, back again. And in fact, here it is right here on the front desk. And so here is the outer portion of the calorimeter. Here is the insulating ring. Here is the inner part of the calorimeter, which we've got to measure again. And then it's the mass. And then there is also water inside here. And so there's a certain amount of water that's contained inside here. And we're going to be keeping track of all of those masses. Now, what we have for latent heats, we're going to be measuring latent heats for fusion, and then also latent heats for vaporization, actually condensation. So for the fusion part, we're going to start with some ice. Now, I tried to hammer down the ice so that there's enough surface area that it would melt in a reasonable amount of time. I'm a little concerned that it's gotten a little drippy. The ice that's going in shouldn't have any liquid water, right? So when we actually transfer the ice, and again, I'm trying to get rid of any excess water that we have on this ice. Maybe I'll try putting it on some paper towel. When I transfer the ice into the calorimeter and then close this off, I don't want that ice to have already melted. The phase transition needs to take place during the time it's in the calorimeter. So anyway, let's take a look and see what we've got here. Here are those little chunks of ice. It's going to have a certain mass to it. Now, I'm not going to try and measure the mass of the ice up front. That means the ice would just be melting on the scale. What I can do is I can put, a few chips of ice in here until I get enough of a temperature drop that I can make some reliable measurements. And then at the end of the run, I can go back and measure how much the mass has gone up. So however much mass has increased for the calorimeter with the water inside of it, how much additional water I have, that's going to be the mass of my ice. And so that's a number that we're going to need to come up with, but it's going to take some subtractions to do that. Now here's the ice. It's starting off at 0 Celsius. So we're just going to say flat out, hey, the ice is going to be at 0 Celsius when it undergoes this phase transition. We're at 1 atmosphere pressure in the room, pretty much. That's where the phase transition is going to take place. So here comes the ice at 0 Celsius. Now, in the calorimeter, we already have some water. And the water's, at room temperature, somewhere around 20 Celsius. We'll get a thermometer, get that measured. So we'll get all the starting temperatures, all the starting masses. We're going to get all the starting temperatures, and then we're going to put ice into the calorimeter. Now, as I kind of hinted at earlier, if I put a little bit of ice in, and the ice melts, but the temperature hasn't come down much, I'm going to need to put some more ice in. I need to put enough ice in that I can actually get several degrees. I want to see the temperature drop by, 5 or 10 Celsius. I don't want to see it just drop by a fraction of a Celsius. That's not going to give me a very reliable result. So anyway, I'm going to put a little bit of ice in, check the temperature, put a little more ice in, check the temperature. It's going to be a little bit more of a trial and error sort of approach. Or not so much trial and error as just incremental. So incrementally, we're going to add some ice, and once we see enough temperature drop that we feel like we can get some reliable numbers, we'll stop and say that's our final equilibrium temperature. Okay, so just adding ice into that. In fact, we can kind of do that right here. We don't need anything any more dramatic than we have the calorimeter, we have the ice chips here. We can open this up and drop a little bit of ice in, swirl it around, watch for temperature dropping. Now on the theory behind this is that as we drop the ice in, the temperature of the water that's already inside and the calorimeter, those temperatures are going to drop. So thermal energy is going to be drawn out of the calorimeter, and it's going to go into these little chips of ice. Now when the ice melts, it's not through, because when the ice melts, it's now become liquid water. But I still want to keep track of the mass of that liquid water because we have to account for its temperature going up. So the ice goes through two steps. It melts, step number one, and then step number two is its temperature goes from 0 up to the final equilibrium temperature. So I need to include both of those effects in the math. So here's the idea. Here's the water going, here's the heat being drawn out of the water, and here is the heat being drawn out of the calorimeter. Those formulas look the same as they did before, and I have all the numbers. By the time I've done the temperature checks, and I can just write down all those numbers. Those I know, I can fill those in. Now, as far as the ice, we talked about those two steps, and here they are. So here is the heat going into the ice. I'm calling that Qx. And here is the mass of the ice. Now, the mass times the latent heat of fusion, that's the portion that does the phase change. Over here is the mass times the specific heat of water times this temperature change from 0 to equilibrium. That's the heat that goes into the ice once it's melted. So I'm accounting for that additional heat going in to bring that portion of the water up to equilibrium temperature. So again, it's a calorimeter. We're imagining that all the heat transfers that take place transfer within the calorimeter. So we've written that down right here. And then I'm taking this equation and flipping it around and solving for the latent heat of fusion. And I hope I got both the algebra right there. I think I've got it correct. And so the latent heat is going to be the portion of heat that goes into the ice. But first of all, we have to subtract off the effect of the additional heat that went into just heating up the melted ice. So that's what this term is keeping track of. The data tables, they look kind of like they did with specific heat. We made a big deal of specific heat, that we had like, you know, a lot of numbers to keep track of. And we have kind of the same thing going on here. We've got the mass of ice that ends up going in. And remember, we don't have that until the end. I put that here at the first of the table just to make it look like the specific heat problem. But maybe that's not a good idea, because this we really don't know until we reach that final equilibrium temperature, and then we pull out the calorimeter cup, carry it over to the scales, find out how much additional mass is present. That must have been the mass of the ice that melted. So here's the mass of the ice. Here's the mass of the water that starts out in the calorimeter. Mass of the calorimeter, all the starting temperatures, the final equilibrium temperature, the Q's that we've defined up above, and then finally the heat of fusion. We want to take 3 runs. That's become kind of a tradition with us. So we're going to do 3 runs. We're going to end up with 3 values here. And then we're going to do an average. right? So we'll come up with some kind of an average number from that. That's our overall results for the day. Okay, I think everything's taken care of there. For the results table, we want to list the results that we've ended up with for the latent heat of fusion and compare that with the accepted value and then do a percent difference. This is, I'm going to say this is not one of the most, it's not a high precision measurement. You can imagine that the ice going in, some of that surface is already melted. It's hard to get the ice to not have any water on it as it goes in. That's a little tricky. The temperature differences that we end up with here can be pretty small. It's not like the temperature's changing by tens of Celsius. It's usually in the single digits. So anyway, we're a little more, a little less certain. We got some more limitations here. We do want to get those temperature measurements right to the tenth of a Celsius. Okay. All right, so that's what vaporization looks like. Now let's move over and take a look at, or I'm sorry, that's what fusion looked like, or melting. Let's find out how much heat there is in vaporization. Now we're actually not going to go in the direction of vaporization. We're going to go in the direction of condensation. So we're going to take water vapor. We're going to generate some water vapor, same as we did back in the first lab of the semester when we did the thermal expansion. We had steam generators, but we're going to bring out the steam generators again. So we're going to bring out the steam generators and generate some vapor that's going to come shooting out of the vapor hose. And well, let me just grab one of those and bring it up here. I've got it back here on the table. See if it's ready to go. See if it is safe to bring up. I'm hoping it is. It has. I started heating this up a bit, but it seems it's not that hot right now. So what we want to do with this is, instead of putting the ice into this, same setup as before with the calorimeter. So we're going to start with something near room temperature. But what's going to happen this time is we're going to put this on a hot plate. That was actually a little warm that time. This is on a hot plate, and we're going to have steam shooting out of here. So what we can do this time is we can direct that steam into the water. Now, I haven't stuck this down inside. No, I guess I can do that. So I'm going to stick this down inside. What we want is the steam coming out to bubble through the water. If the steam's just inside the calorimeter, but not really down under the water, it's not going to condense. We need to have that, as you can see that this was down into the water. So we're going to need to have that steam bubble through the water. If we can get it down below the surface, I just push this down to the bottom of that calorimeter cup. We're going to get the steam to condense. The steam will be condensed. It's not going to come bubbling up through the surface. Okay, so that's the plan. Now, that works the same way as the ice in that, well, let's just do the comparisons here. This time what's going to happen is the thermal energy, instead of being drawn out of the water in the calorimeter, it's going into the water in the calorimeter, right? Instead of seeing a temperature drop to equilibrium, we're going to see the temperature increasing. Now, kind of the same as when we talked about, well, I could just keep adding more ice and bring the temperature lower and lower. I could keep adding more steam and keep bringing the temperature higher and higher. Now, each of those approaches, we don't want to go too far with these, because at some point, this is going to heat up to the point where, you know, the calorimeter is not ideal. It's going to begin losing thermal energy to the environment. We don't want that to happen. So anyway, again, we'll look for a, I don't know, we'll see, maybe 10 or 20 Celsius increase in temperature. That's enough. And then we'll stop the lab. And same as before, in order to find the mass of the steam, same as the way we found the mass of the ice, is we wait to the very end. Once we've decided, okay, I put enough steam in there, we're done, then I can pull out, and I want to get the equilibrium temperature. Then I can pull out this calorimeter cup, take it over to the scale, and see how much additional mass there is. I'm going to attribute that extra mass to the condensed steam. All right, that's the idea. Data tables are going to look very similar. Ooh, I guess we were still at the Q's here. So this is now the heat going into the water and the calorimeter. This is the heat coming out of the steam. Now, just like before, there are two portions to this. There's a latent process. We're assuming the steam coming out is right at 100. Okay, so which seems like a pretty good approximation. It certainly is in the process of condensing as it comes through the hose. The portion of the steam that reaches the water and adds to it, we want that to be as best possible at 100. So we really want the steam coming out pretty forcefully. Let's see, and so there's a latent portion to that, and then once the steam has condensed, it's going to drop in temperature from 100 down to the equilibrium temperature. So this is the heat coming in from the portion of steam. Now, same as before, we're going to say that the calorimeter is containing all the heat. And then finally, we're going to solve for the latent heat of vaporization. Data tables look very, very similar. I think we have all the very same entries that we had before. And then here's our diagram for how this is all working. So I think that covers it all. Let's go over to the table and get the close-up look at how this is going to work. We'll do a run and see what this is going to consist of. All right, here we are back measuring the mass of the water that we're going to be starting with. We've got it inside the calorimeter here, the inside cup, 217.9. We're going to move that over, put it inside the calorimeter, and then what we want to do is we want to get a starting temperature for this. So make sure that we've got our thermometer down into the water, and I'm going to get a reading on this, and then we'll be ready to start. And then I'm going to be taking ice from here and dropping that ice into the calorimeter. Now in the backdrop here, I've got the steam generator starting. So I've got the hot plate out, and I'm starting to get the water up to temperature where we can get some steam, have some steam ready to move on to the next part of the lab. All right, the temperature started out at 15.2 Celsius. So now I am ready to introduce some ice. Now I don't need a real lot of this. Ooh, and I got to get back. This is getting kind of drippy here again. So I need to come back and dry some of that. I'm going to put a couple chips inside. Start with that, and we'll see what that final temperature works out to be. So the ice is melted. I put a little more ice in than I usually do on these runs. I took the temperature all the way down to 6.3 Celsius. We'll see if that was a good idea. I'll have to try some different numbers on the other runs. So I'll do 2 additional runs and see how that works. I put a little more ice than usual to see if I could bring the temperature down and get a larger temperature drop in order to possibly get some more reliable results. Meanwhile, it sounds like the steam is almost generated in the other device, so I thought I would wrap things up over here on the fusion side and get ready to add some steam into the calorimeter for the vaporization calculation or measurement. Oh, there it is. It starts steaming right away. Right as I was saying, it sounds like it's going to start to steam any minute. There it is. So I'd better get set up for that. Okay, so I put the hose from the steam. It really gets hot, so I have to be a little careful here with it. I didn't want to take pictures, and anyway, I've got the steam. It was coming out very forcefully, and if you listen, you can hear the steam bubbling through the water as it comes back through. So Anyway, I'm going to let this thing run for a bit, and then we'll see what temperature we've gotten up to. And also, I should mention one more item here. I realized that since I was down below room temperature with the ice, I went ahead and rather than starting with a new sample of water, I just got a measurement of the mass with everything included. And now I am going to start below room temperature. That's going to let me add a little more steam. So that will probably help, starting at a lower temperature and then running up to a higher one. In fact, right now, I am planning on alternating. I'll probably go back and forth between adding ice and adding steam. This should, I'm hoping, will give us wider temperature differences and give us some more reliable results. So I'm up to a temperature somewhere around 25, between 25 and 30 Celsius. I'm going to get ready now. I'm going to pull out the steam. I'm going to turn off the hot plate. I'm going to go back and do an ice run. So this kind of wraps everything up, I think, for the video. I think what we've done is we've seen what happens with the ice, we've seen what happens with the steam, I've got all the numbers written down here, and I will get those put into notes and get those posted on Canvas. All right, thanks for coming to this week's lab. Hope that has been useful. Any questions, let me know, and we'll get those questions taken care of.